Szanowni Państwo, chciałbym Państwa bardzo serdecznie powitać na uroczystości wręczenia medalu imienia profesora Włodzimierza Kołosa. Z tego powodu, że część naszych kolegów, naszych pracowników nie mówi jeszcze po polsku, bo mamy sporo gości z zagranicy, pozwolą Państwo, że za chwilę będę mówił po angielsku. So first of all, I would like to welcome Professor Izabela Nowacka, the president of the Polish Academy of Chemistry. I will also very warmly welcome the winner of the Kołosa Award, Professor Jacek Klinowski from the University of Cambridge. It's a great pleasure to have you here again. We met about 1 year ago. Professor Klinowski is also the laureate of the honorary doctorate of Warsaw University. So to some extent, Professor Klinowski is also a member of our society. I would like to very warmly welcome the representative of the family of Professor Włodzimierz Kołos, astrophysician, Professor Robert Kołos. It's also a great pleasure that you find the time to be present here. As I said, let's make according to the tradition, and we have during this ceremony free speech. First of all, some, of course, only selected achievements of Professor Włodzimierz Kołos is presented, and I asked to do it Professor Grzegorz Hałasiński, and Professor Grzegorz Hałasiński is always the chairman of the award committee. Then I will ask Professor Krzysztof Woźniak also only to present some selected achievements of our laureate. And after that I ask Professor Izabela Nowak to come here and to present the award with me to Professor Jacek Klinowski, and the ceremony is finished by the traditional lecture of the laureate, Professor Jacek Klinowski. So as you see, we have a very rich, how to say, program of this ceremony, so I don't want to prolongate it. So Professor Hałasiński, the floor is yours. And I can also give you a microphone if you need it.
Well, I don't know yet. Either this one or this one.
Oh, it depends on
I
you,
don't
but
need
I
the
can
microphone. This is up to you actually to choose.
I could get an organizer, but I
should have to say switch off the second, because it works, it not works properly if you have two microphones.
What about that? Do you hear me? Yes, I hear myself, so probably you hear me too. Okay, is my head low enough not to disturb your viewing? Okay. Somehow. Oh. I'm sorry for the crowded desktop, but let me do a little trick so we could. Anyway, I think I have to find out what this is. This one. Probably the best known achievement of Professor Kołos was that he performed first calculations of the dissociation energy of molecular hydrogen with accuracy better than the best experimental determinations of his time. He was among pioneers of applying programmable computers in chemistry. Before him, actually, this was, nobody actually bothered really, and he was one of the pioneers. Next, a connection of quantum chemistry to methodology of theoretical physics. He showed that you can describe chemistry in terms of quantum mechanics. And last not least, he developed theory of intermolecular interactions with short-range forces included.
Now, the subject of my talk is enumeration of possible new structures. So my main interest is the reason for this complexity everywhere, including in chemistry. Now, why do these things exist? Well, they exist because they can, okay? And they can because the rules leading to their creation are very simple. And I will show you what I mean. Let's imagine that I take a part of it, a little square somewhere, and enlarge it 10,000 times. What do I get? I get the same. You see these strange objects appear here, and they appear there forever. It's infinitely complex, this fractal. Mandelbrot himself had no idea what it looked like because he could not calculate sufficient points. He knew that it was something very, very odd, but could not calculate the sufficient number of points. Now, Lorentz oscillator is another example of complexity. Look at this. There is a point in space, and there are three equations describing how it should move with time. This is the change of the x coordinate, this is the y coordinate, and this is the z coordinate. Now note that they are not separate because x appears also in the equation for y. They are not separate. Well, I dare not touch this because, you know, it's very strange. Now, this square can combine further to build these cubes, and objects like this in the middle is a cage which fills space by itself, very rare property, and double membered rings. And you have structures like zeolite A and forgesite. Zeolite A does not occur in nature, but is produced in megaton quantities. Why? Because it's used for separating oxygen from nitrogen. The openings in the channels are the size of small molecule, and it preferentially absorbs oxygen. Now, it's also used in washing powder and such things. And on the right, you have forgesite, which is a very, very rare mineral, but it's also manufactured on megaton scale, because it is a catalyst in the production of oil. So this statement, 28% of world's petrol was created at this desk. This is Dr. Weiss's desk at Global Oil in America. And he discovered that zeolite Y was a cracking catalyst. Cracking means splitting large molecules, because oil is something, large molecules, rather unpleasant. If you cut them into pieces, you can get petrol and other things. Now, what is petrol? It's 5 to 10 hydrocarbon without oxygen, 5 to 10 carbon atoms. So, our results apply to various classes of structures. We have actually stopped this because I think that the most important thing for a scientist is to know when to start working on something, and even more important, when to stop. But since we have published the way to do this, anyone can enumerate structures. I'm not interested in details. I'm working on something quite different. So this is all I have to say. I would just like to thank my dear wife, Jacek Klinowski, for supporting me. Without her, I would not have the Kołosa or anything else.